We have arrived at section 4.5, which discusses the concepts of basis and dimension. So let's start with a definition. So let V be a vector space and let B be a subset of V. Then we say that B is a basis for the vector space if it spans V and if the elements of B are linearly independent. So you can think of this as being a basis, as being a set of building blocks for the vector space. And the first condition here, that it should be a spanning set, this basically says that the set is not too small. There's enough elements in B that you can build everything. Everything in B can be constructed just from the building blocks inside B. So that's right. This condition means basically that it is not too small. And then the second condition is that it should be linearly independent, which is the other one. So it says that the set is not too large. And what does that mean? So you recall that when you have a set that's linearly independent, and then if you consider the span of all the elements in that set, then the expansion coefficients in any linear combination are unique. And this is extremely convenient because then with every vector in V, we're now going to identify a unique set of expansion coefficients in regards to the basis. And there will also be connections between the dimension of the vector space. So this is something that has sort of been percolating around already. And we're going to get soon to a formal definition that says that the dimension of a vector space is the number of elements in the basis. And this, of course, so the subtlety, the reason I'm not just writing that down right now is that you could envision that you had a vector space that have two different bases with differently many elements. If there's one basis that has 7 elements and another one that has 10, then what is the dimension? So it turns out that for a given vector space, all bases have the same number of elements. But that's something we're going to need to work up towards. We're going to need to prove that statement. But before we get there, let's start with some examples just to make sure that we understand the concepts here. So let's start with the very basic example here. So we have our standard vector space R2. So here we have the plane, and then you have our two basic vectors, E1 and E2. And they together form a basis. So this we're going to define as the standard basis in a little bit. So let's just verify this. This is trivial, but let's do it just to make sure we get the concept. So if you pick an arbitrary x, in R2, then the question is, can we write x as a linear combination of E1 and E2? And of course you can, because we can write x like this. So I just split x1 and x2 into two separate components, and then I write that as x1 E1 plus x2 E2. And you see that this is clearly unique. There's no other way of writing the vector x. So these two vectors, we already verified that they are linearly independent, and they certainly span all of R2. So they form a basis. But the basis is not unique. So almost invariably, if you have a vector space, you can have lots of different bases. So another one is given down here. So we have the vectors V1 and V2, and they are certainly very different from E1 and E2 that we saw before, but this set is also a basis for R2. So how do we verify this? So what do we need to consider? So again, we start the same. So you fix some general vector in R2, and then the question is, are there coefficients such that x is equal to C1 V1 plus C2 V2. So this would speak to whether it's a spanning set, and then the second question is, are they unique? And that question answers whether the set is linearly independent. So let's see. So now this equation here, let's call that star. So I could alternatively write star using matrix notation as 1, 2, 1, 3 times C1, C2 is equal to X1, X2, which is the same as the equation A, C1, C2 is equal to X1, A2 for now the coefficient matrix A is a matrix that has V1 and V2 as its columns. And now the interesting question is A invertible or not? So for a 2 by 2 matrix, it's easy to check. Compute the determinant. This is 1, so A inverse exists. And this means that this equation here, let's call that star star, that now I can pre-multiply star star by A inverse to get C1, C2 is equal to A inverse X1, X2. So now we have both existence and uniqueness. And uniqueness is also okay. So yes, this is also a basis. The vectors V1 and V2 also form a basis for R2. So important point here, a basis is typically not unique. All right, so what if I add a third vector? So this is the same example as before. We're still working with R2. We have the same vectors V1, and I have the same vector V2, but now I throw a third one, V3, into the mix. So now we know that V1, V2, V3, it is a spanning set. So this is okay. So which condition was that? So condition 1 is okay. And this is not surprising, right? So the question was, if you think of a basis as a set of building blocks, do you have enough? And we know that V1 and V2 is enough by themselves. So throwing in an extra, it doesn't hurt. It doesn't help either, really, in this case. But it certainly doesn't hurt. B is still a spanning set. But so you don't have too few elements. But in this case, you do have too many. Because now, this is not a linearly independent set anymore. We already discussed this, that if you have a set of 3 vectors in R2, then necessarily one of them must be linearly dependent on the others. In the current setting, you could phrase this as asking, so if we want to solve, how does this come up? Well, say we want to solve, so I should have started given vector x. Can we find coefficients C1, C2, and C3? Yes, we just established that we can. Now we're considering the question, are they unique? So now remember that equation, let's try to stick to the same color. So this is equivalent. So now I have a coefficient matrix like that. And you see it's impossible for this linear system. So the linear system here, it cannot possibly have a unique solution, because if you look at the RAF of the coefficient matrix, it can have at most 2 pivots. So there must be a free variable. At least one What this means is that C1, C2, C3 are not unique. So 2 fails. This is not a basis. All right, so now let's move on to R3. So in R3, suppose I have 2 vectors. So these are old acquaintances. They've come up in several examples before. And we verified that these 2 vectors are linearly independent. So B is linearly independent. So condition 2 is okay in this case. But they are not a spanning set. So condition 1 fails, and this is not a basis. So as an aside, you might want to think about, so why is that? How can I just declare that they are not a spanning set? Well, one way to prove that is to say we compute the RAF of the coefficient matrix. So the question is, does the equation, so the equation we want to solve is this. So here is the coefficient matrix A. And now I'm just asserting, well, there exists x1, x2, and x3 such that this does not have a solution. And one way to prove this, if you want to prove this, is to let, if we transform this to the RAF, so let B equal to RA be the REF of A. So in this case, since these vectors are linearly independent, we've already verified that, we know that the RAF looks like that. Right, so now I can write down a linear system that does not have a linear solution. That does not have a solution like this, but this is not the right system. I have the coefficient matrix B there, but now if I pre-multiply this by R inverse, I get R inverse 1, 0, 0, 1, 0, 0, C1, C2 is equal to R inverse 0, 0, 1, and now this is A, and I pick that as X. Then the original linear system does not have a solution. Okay, so the last little bit here was just a recap of how can I say for sure that there exist right-hand sides such that this linear system does not have a solution, which is to say that the columns of A do not form a spanning set. Let us continue with another example. So this is a pretty general example. So suppose our underlying vector spaces are M as in Martin, and then I have n vectors, v1, v2, up to vn. And now the question is, what can we say about whether B is a basis for V? So now all we're going to do is generalize the discussion from the last couple of examples. So first of all, suppose that we're in the case where M is smaller than n. So we have more basis vectors than there are elements in a vector in V. So this is the case we saw on the previous slide. So now the argument works exactly the same as for the case where we had 3 vectors in R2. That in this case, it's impossible for the linear system that determines the coefficients to be unique, so we never have linear independence in this case. So cannot have, let's phrase it like this, B cannot be linearly independent so one of the conditions must fail. Let me go back and see which one. So this was condition 2. So 2 fails. So not a basis. So in the other case, this is the other example we had. So this is a generalization of the situation where we were in R3 and we had just 2 elements. In this case, B cannot be a spanning set. So condition 1 fails. So again, we have not a basis. Now, if I have equally many, if the M and N line up, then now I have a fighting chance, because now my coefficient matrix is square. But notice that square is not enough. I need that square matrix to be invertible for this to work out. So for instance, let's do a little quick example. I'm going to delete this in a second. But say you're in R2 and you have the vectors V1 is, say that, and V2 is this. Now, you have 2 problems. On the one hand, this is not a spanning set, because anything, if you have any linear combination of V1 and V2, then this will be, the second entry will be 0 necessarily. So it's not a spanning set, and these 2 vectors, they're linearly dependent, so you can never have uniqueness. So in this case, what we need is that for the coefficient matrix to be invertible. So let A be the matrix that has columns V1, V2, up to Vn. And now if the determinant of A is not 0, or let's phrase it like this, determinant of A is not 0 is equivalent to B is a basis. So basically the lesson here is that in order to have a fighting chance, then a set of vectors in Rm must have precisely m components. But even when you have the right number of elements, you also need for this set to be linearly independent. And notice it's sort of the same thing, or it's exactly the same thing as happened when we talked about linear systems with a square coefficient matrix, that you have a unique solution precisely when you always have a solution. So let's continue with our next example. So here we have the general vector space Rn, and then there is a basis that's particularly nice. So it is just these vectors. We've seen this before. So it's the one that consists of all zeros, except they have a 1. Ej has a 1 in the jth entry. So this is a particularly common and particularly nice basis to use. It's often called the standard basis. That's the terminology used in the book. I personally usually call it the canonical basis, so I may use that term every now and then. I'll try to remember to say standard basis, but if I say canonical basis, you should know it's exactly the same. There are canonical bases for many different sets. If we look at, for instance, the set of all matrices, let's look at 2 by 2 matrices here, then this is a spanning set for these matrices, as we discussed in a previous section. They are clearly linearly independent, so therefore they are bases. And this particular set of matrices is sometimes referred to as the standard basis for the set of all 2x2 matrices. So I did it for 2x2 just because it's big enough that it illustrates the principle, but it was not too much writing. Of course, you can do this for matrices of any size. Here is a paragraph that I copied from the book. So here is a set of all 3x2 matrices. And here we have, right, so this would be psi 1, 1. This guy would be psi 3, 2, and so on. So these form the standard basis. For polynomials, I'm sure you can guess what the standard basis is. So Pn has the standard basis consisting of all the monomials. So 1x, x squared, x cubed, all the way up to xn. So notice that it has n plus 1 elements. So Pn, as we've seen before, well, we haven't defined dimension before, but you sort of can intuitively probably sense what it means. So there are n plus 1 elements in the standard basis for Pn. And then we have our one infinite dimensional example of a vector space that we've talked about, which is P, the set of all polynomials. And here, of course, the standard bases are also the polynomials. It's just you have to continue and include all of them. So we've already talked about this, but let's just re-emphasize this point that a basis is not unique. So these guys here, they are bases for the various polynomial spaces, but there are many others. So here is the standard basis for P1, but there are lots of others. So this is also a basis for P1. There are tons of different things you can do. You can do 1 plus x. That's a basis. You can do x. As long as they are linearly independent, it's fine. So what you cannot do, for instance, is you could not do, this would not be a basis because it's linearly dependent. And yeah, you cannot have any set with just one element is disqualified, any set with 3 elements is disqualified, or more. Of course. Okay, so here is an important theorem. This is sort of the centerpiece of this section. So I've labeled it Theorem X because we're going to be referring to it going forwards. It has it's a slight reformulation of a theorem in the book. In the book, this goes as lemma 410, but it's not exactly. I rephrased it a little bit because I think the book does this in a slightly klutzy way. But if you want to look it up, then it's lemma 410. So what does this theorem say? It says that if we have a vector space V with a subset S, and now there are 2 assumptions on S. One is that it's finite, the other one is that it's a spanning set. Then if you take any set that has more elements than S does, so recall this means number of elements in S. So if you take any set that has more elements than S does, then that is necessarily a linearly dependent set. So in order to prove this, we will use a slight lemma that sort of says that this theorem holds true for Euclidean space. But it's a very simple technical lemma to prove, so we'll quickly prove the lemma and then we'll use that to prove the theorem. So the lemma says the following, that if you take a matrix C, so notice here that C is rectangular. It looks like this. So it has n columns and m rows, and m is larger than n, then you can always find there is some vector d that's not the 0 vector, such that this works out to 0. And let's prove this. So let's label this equation star. Now, if I just take the transpose of star, I get another equation which says the following. So now C transpose is a matrix of this size, and D transpose is a vector, like so. And now we recognize this, that this is exactly the kind of linear system we know how to solve. So it's homogeneous, and it's necessarily, it has infinitely many solutions, it has non-trivial solutions, because there are more variables than there are equations. So this is a homogeneous system. So it's consistent, it has solutions, and there are non-trivial solutions. You remember the way we proved this is that if you reduce this to its RAF, then you're going to have some pivot elements, but even if you put one pivot element in every row, there's just not enough of them. There's going to be some columns that are not pivot elements. All right, so this is just a review of stuff we already know. So, right, so given a tall rectangular matrix like this guy C, you can always find this matrix, a non-zero matrix D, such that when you multiply them together, you get 0. All right, let's delete the proof. And now we will turn to the proof of the theorem. Let's use a different color. So let us prove the theorem. So the first thing we'll do is that we'll name the elements of S. So let S consist of the vectors v1, v2, up to vn. So now our claim is that if you have a set with m elements where m is larger than n, then that is necessarily a linearly dependent set. Let T, all right, so how do we do this? Say T1, T2, up to Tm be a set with m elements for m greater than n. Then our claim is that T is necessarily linearly dependent. All right, so now we need to use our assumptions. We need to use that S is a spanning set. So since S is a spanning set, we can write, so each vector Ti I can write as a linear combination of the vectors Vj. Right? Because the vectors V, they span everything, so in particular they span the T's. So for each T, I can build each vector T. Sorry, I had a slight glitch with the recording. So to recap, the point was that I can build each vector T as a linear combination of the V's, and the coefficients there are Cij. So then what I do is I form the matrix C here, which is the matrix that has entries Cij. And now I invoke my lemma. So the lemma implies there exist this vector d1 with entries d1 to dm such that dc is equal to 0. And now my claim is that if I form the linear combination of the t's with the expansion coefficients given by the d's, then that will add up to 0. So let's see if that works out. So d1 times t1 plus d2 times t2 so it turns out to be easiest to write this as a sum using this summation notation. So now I'm going to plug in this relationship for the ti's. So then I get that this is sum I goes 1 to m, right? di, and then I get each ti is sum j from 1 to n, cij, vj. And now I just need to change the summation orders. These are finite sums, so there's nothing controversial about this. So I'll put the sum over j on the outside. And then on the inside, I get the sum over I. And then the vj's on the outside. Now, look and behold, each one of these is 0, since dc multiplied together to 0. So this is sum. All right, so t is linearly dependent. And now we have proven theorem X. So here comes the center result of this section, which is to say that for any fixed vector space, all bases have equally many elements. So if we want to make this precise mathematically, then we have our theorem here that says that if V is a vector space that has a finite basis B, or rather, let's not do if statements, we suppose that this is the case. Let V be a vector space, that it has a finite basis B. But when I say finite basis, I mean a basis B with finitely many elements. Then if T is another basis for the same vector space, then the number of elements in T equals to the number of elements in B. Let us prove this. So let B consists of the vectors 1 through n. Actually, I don't think I even need that. I don't need to name them. So let's just say let B have n elements. Now let T be another basis. And now I'm going to invoke theorem X twice. So first of all, so observe that the elements of B are a spanning set. So the elements of B form a spanning set. So that tells us that the number of elements in T has to be less than the number of elements of B. Then theorem X says that the number of elements in T must be smaller than the number of elements in B. since T is linearly independent. Right? Because the theorem said that if you have a spanning set with n elements, then any set that has more than n elements is necessarily linearly dependent. And we know that T is not linearly dependent, so you must have fewer elements. And then for the other direction, you of course just work backwards. So you flip the roles of B and T. The elements of T form a spanning set. And then theorem X says that the number of elements in B must be smaller than the number of the elements in T, since B is linearly independent. Right, so this is very nice. So basically, if you have any vector space, then if you have one basis that has finitely many elements, then every other basis has finitely many elements, and in fact, exactly as many elements. So this means that this number n, the upshot of this is that this number n is unique to the vector space. It's something that does not, it's not a property of B. It's a property, it's not a property of a specific basis, it's a property of the vector space. And now, as promised, we get to our definition of the dimension of the vector space, which looks like this. So let V be a vector space. We are here. If V has a finite basis, then we define the dimension of V as simply the number of elements in that basis. So that leaves the case where V does not have a finite basis, and in that case we simply say that V is infinite dimensional. You can, if you want to be, there are actually all sorts of different types of infinite dimensional here, but that's a topic for a different class. So let's just look at some of our examples we've already discussed in class. So the dimension of R2 is 2, because you recall you have the standard basis. It has 2 elements, and once you've proven that there is one basis that has 2 elements, we know that every element has 2 elements. All right, so the fact that Rn has dimension n should not strike you as being surprising at all. For the polynomials, you have this slight quirkiness that the set of all, well, so if we take the quadratic polynomials, well, it has the basis 1x, x squared, which has 3 elements. Now you see this we've sort of danced around this, but I've tried to avoid using the word dimension. I've failed a couple times, but I've tried to not mention it. But you see a quadratic polynomial in general can be written like this. So there are 3 free coefficients in it, C0, C1, and C2. And another topic that we've danced around is that P is in some sense associated with the vector of these elements, right? So there's some sort of close connection between this polynomial P and the vector C0, C1, C2 in R3. Right, so we'll return to that question later. So similarly, the dimension of Pn is n plus 1. So P here, well, I shouldn't really write this. I should write rather P is infinite dimensional. Of course, you can maybe write infinity there, but there are some subtleties about that notation, so I'll try to avoid it and simply say infinite dimensional whenever that's the case. So just one more, the space of matrices. Recall there are m times n, because that's how many elements there are in the standard basis. What about upper triangular? So if you take, say, all 3 by 3 upper triangular here's a good exercise. I guess I'll tell you the answer. So the dimension is the number of free variables here, which is 6, right? So an upper triangular 3 by 3 matrix, it's specified by 6 numbers. So just think for 2 seconds about what is the standard basis for this space. I mean, if you don't see it immediately, you'll think of it quickly. It's not a hard question. Here's a theorem that's really just the mildest reformulation of our basic theorem X from before, but perhaps just write it down to make sure that we remember this. So if you're in a vector space of dimension n, then this theorem has 2 components. So first it says that any spanning set must have at least n elements. And any linearly independent set has at most n elements. That's the second part. So this is it's exactly theorem X under the very, very mildest of disguises. So let's prove A. Suppose S has n elements, then, so now we have a spanning set no, sorry, let me redo that a little bit. We suppose S has fewer than n elements. We'll get a contradiction from this. Then by theorem X, says that any set so theorem X says that any set with more than S elements is linearly dependent. And this is a contradiction. Since a basis B for V has n elements and is linearly independent. And the second part works exactly the same. So this is directly theorem X. We don't even need to do any contradictions or anything. So theorem X, or maybe we should at least write down what we're doing. Let B be a basis for V. B is a spanning set with n elements. So theorem X says that any set with more than n elements is linearly dependent. Right, and that does it, because T is linearly independent, so it cannot have more than n elements. The final theorem we'll go over in this section. This has been quite a long section, so make sure you go over this carefully. Says that if you have a vector space V that has a, okay, so we have V here. Now if W is a subspace of V, then the dimension of W is bounded by the dimension of V. So you have this important relationship. And you see the two notations, that the inclusion sign, the subset sign, almost looks like the greater than or equal to sign. And it is because there is a connection between these concepts. They're different, but if you talk about linear spaces, if you talk about vector spaces, then a vector space as it's a subset of another one, if that holds, then the dimension of the subset is bounded by the dimension of the larger space. Right. And if you have equality, if they happen to be the same, then the only possibility is that the two spaces are the same. Then the subspace is equal to everything. There is no way to form a strict subset of a vector space that has dimension that's the same as the original space. And this, for the proof, this is left as an exercise, and it is exercise 21. So this is an important exercise to do. This will work you through a lot of the concepts we've covered today. All right, that concludes the lecture, I believe. Yes. All right.